This is a pre-lab for Chemistry 151 lab. I'm going to go through the first two experiments real fast. These are short, so that's why I'm doing two at once. So let's look here. This first one is safety, and safety is important. I mean, normally this would be a long time. I would, if it was face-to-face, we would sit down. I'd spend about a half an hour talking about safety. Although, well, you're still responsible for safety, even though you're doing this at home or wherever you're at. But I'm not going to be there to look over your shoulder. But safety, you are responsible for this. This kit is pretty safe, though. I mean, it's still dangerous. I mean, you can still hurt yourself, but there isn't anything really, really toxic like you would see in a chemistry laboratory, like a traditional chemistry laboratory. So, it talks about Frankenstein. So, but this is nice. So even though you're not in my lab, you can still touch and feel the chemicals. So, safety equipment, glasses. This is your most important. Eye protection. Eyes are very sensitive. Your skin is a couple cells thick of dead keratinized cells. So I mean, your skin's pretty tough. I mean, you got a lot of protection here. You know, here I am just poking my cheek. Doesn't really bother me. I start poking my eye, that's gonna hurt. Your eyes have tears and then stem cells. There's about 3 layers thick of stem cells. So it's not, you're not looking at a whole lot of protection there. You get anything in your eyes, it's gonna hurt and it might damage you permanently. And so various things. So if you do get some in your eyes, make sure to flush your eyes for a while. 20 minutes says. So, in general, know where these things are. Here are the safety rules. Always wear glasses. Contact lenses, not a good idea. You can get your contact lenses diffused to your eyes if you get, especially alkaline chemicals. That, and when you get something stuck in your eye, first thing you do is you shut your eye, and if you're trying to clean it out, trying to flush it out, you have to force your eye open, and if you have contact lenses, it makes that difficult. So don't do unauthorized experiments. Don't just start mixing random stuff together, see what happens. Not a good idea. Don't do this alone. You know, this is kind of like snorkeling. Have your buddy, have somebody there ready to help you if you need be. Also, for those of you that have kids at home, be careful. Your kids don't mess with the chemicals, so be mindful of the children. Also, don't eat, drink, or whatever around the chemicals, smoke. It's because, a lot of things look like water. So, sulfuric acid looks just like water. So, my mother used to tell me this, she's a chemist, she told me this limerick, little Timmy had a drink for he will drink no more, for what he thought was H2O is really H2SO4. So, be careful of that. Although this is not the laboratory, this is like a chemical laboratory defined by federal law. You shouldn't eat, drink, or smoke around it. Smoking just because you get stuff in your hands and drawing on the cigarette. And sometimes things can be flammable as well. Let's see here, where are we at? Keep your area free of clutter, make it clean. So clothing. Clothing is personal protective equipment. You'd rather ruin clothes than ruin your skin. Know where things are at your home, your showers, so if you need to wash off fire extinguishers and your sinks. Go through the experiments, look at the pre-lab, this type of thing before doing it. That'll help you to not make any mistakes. Wash your hands before and leaving the lab, especially before you eat. Long hair, I don't really have that problem, so I actually have never had that problem, so yeah, I can't really empathize with you on that. Don't do anything, no horseplay, sort of things. Handling the chemicals, be very, very careful when you handle them. So for acid to water, it's because water and acid mixing together is exothermic, produces heat. So it's better to add the acid to water so it's a bigger heat sink, if you wonder. This is just general chemical stuff. If you don't return the chemicals to the bottles. This is more for research stuff, so you don't contaminate things. Properly dispose of chemicals, because there's some things you should not put down the sink. Arsenic, for instance. You don't have arsenic in the lab, but if you're working with arsenic in a lab, in a real laboratory versus at home, I guess we don't have arsenic here, but you don't want to dump that down the drain. So it's better to dispose of it properly. So keep things clean. You can read these yourself, I guess, more or less. But and MSDS. So if you have any questions about the safety, MSDSs are a very good one to look at. They have a lot of information on there. So although the laws are going to change soon, they're going to be called SDSs, safety data sheets. Not going to use. They're dropping the M for some reason, but for right now, in the time that this is recorded, MSDSs are still there. So how to respond to accidents. So spills, clean it up right away. We don't have that much stuff. If it's an acid, use baking soda. I do that in the real lab too. I actually also have a bucket of sand that's calcium carbonate that can also get rid of big spills. Baking soda, acid, vinegar if it's alkaline. It's a good way to do that. And depending on the spill, I mean, like this is a small kit, so you don't have to worry that much. If it's a big kit, if it's a big area, like say you're working in a garage and you drop over a 5-gallon container of gasoline, that's something you might want to, open your garage door and let it air out or something. That's a little more dangerous, and the fumes can harm you a lot more. So be careful. We were talking about the eyes. Don't eat stuff. If you happen to eat something, or your kid eats something, check the material safety data sheets. I mean, don't just go ahead and do stuff like, for instance, if you drink gasoline, you're not supposed to throw it up because it can aspirate your lungs and coat your lungs. For instance, you might from that it'll tell you what to do on the material data safety data sheet, but in general, so I mean, it's not just like the one response for everything. There's differing responses. So burns, cuts, fire, so general things you have here. So you have these questions on the answer sheets. So what should you do? Always wear, glasses. You add acid to the water, dispose broken glass, carefully in a trash container. And if you spill chemical in your hand, rinse it out with water for a while. There are some chemicals that this doesn't always hold true for. Hydrofluoric acid, for instance, used to use calcium glutamate, but there's no hydrofluoric acid in this. Oh, no. That's a very dangerous and scary chemical. But I'm just letting you know that in other situations, there are various things for other chemicals to do. So go check over your kit. Make sure you have these things in your kit, because sometimes you don't have them. So if you don't have them, let me know, so we can take care of that. So let's go on to the second pre-lab, because the first one's pretty easy. The second one's short too. So of course this is one you don't really have to handle stuff. This is more information, and we're going to look at the scientific method. So let's see if things can be testable. So the whole idea with science in this age of reason is that we base our knowledge off of its experimentation rather than ideas or philosophy. So if this is ancient Greece and I was Plato, I would be like, well, let's talk about how things should be. And this is not ancient Greece. This is after the second millennium. So we base our knowledge off of what we can see, feel, hear, and touch, and measure experimentally. So that's a very big difference. It's relatively new in the world of civilization, but it's also one of the reasons why we've had such rapid development in our technology over the past 150 years or so. So hypothesis is a educated guess. A null hypothesis kind of is counter to that. So don't always have to have a null hypothesis. This kind of more or less goes away as you advance in science, but this is kind of, one way or the other. So experiment, you test the hypothesis, and so experiment must be reproducible. The scientific method is you take observations and then you make a hypothesis, and your experimentation tests that hypothesis. And they have to be reproducible. If it can't be reproducible, it's no good. And test one variable time for this class, that's valid. If you go further on, it's not possible to test one variable time. It's like, so if you're making something big, like if you're working at a distillation plant, making gasoline, you can't test one variable at a time. Sometimes if you do multiple variables. But for this class, do one variable at a time. It's small. It's easy to deal with this. Chemistry can be fairly exact. So that's one nice thing about chemistry, is that we're very exact, very controlled. But this is not always going to be true. And intrude to control, so you know something's happened. This is like when you do a drug study, you have a placebo. So, and the control is, well, I'll show you when later on talk about plants. If you add nutrients to plants, the plants grow. If you compare it to one that you do not add nutrients to. So independent variable, dependent variable. Independent variable you more or less don't have control over. The independent variable is also on the x-axis. Dependent variable depends on the independent variable. That's on the y-axis. Like y is a function of x. Y depends on x. X just grows. Y depends on x. So data collection, various things. Tables. So for this one here, this is, I told you about the plants. So the day, time here, time is the independent variable. We don't have any control over this. The dependent variable, y, is the height. So the height depends on the day. You can see this moves, and then we have a graph. Jumping the graph, coming over here. Here's a graph. Here is the time, is the x-axis. The height is the y-axis. So y depends on x. The independent variable, the dependent variable. That's what everything works there in the graphing coordinates. So you can have bar graphs. Here's another one you can have. So if there's not really a relationship, you can go on. That's one way to go. So we can interpret the results. So then you look at it. You can look at pictorially. I mean, whatnot. You can see here top speed, different cars. So I guess you can say here car D is the fastest. Here interpret this. Well, adding nutrients helps things grow faster. Of course, this is a sample size of 2. In a real experiment, you're going to have a much bigger sample size. 2 is not a very significant sample size. So here, oxygen versus number of fish. So this is going to be the independent variable. This is dependent. Something to note, though, when you do this, you're going to see something like a step function. So you're going to come along. Maybe something you should think about is, do the fish need to have a certain amount of oxygen to survive well? So that's a very common thing. That not every function is going to be a smooth, continuous thing. You can get functions like that. So look over this. And these exercises, try and decide which ones you can test. Some things you can test, some things you can't test. I mean, there's nothing you can do about that. So look over these, and then fill in the answer sheet, and then email them to me. Let me know if you have any questions, and hope you are enjoying the lab so far, although we've only gotten through 2. So, goodbye.